Chapter 17, 18, 19, and 20, like I say, all go together. We're going to be talking about thermodynamics and sort of thermodynamics-related things that are sort of associated and all sort of build. Chapter 17 specifically feels a little scattered to me. Like, we're going to go from one slide, particularly this slide, directly to the next one. You're going to be like, oh, well, that seemed like a non sequitur, okay? That it's sort of a preliminary chapter that's going to give us some of the basics. There's going to be things in here you're like, oh, I did this in high school. Why is he talking about it? I just need to get everybody on the same page, okay? So be a little patient with chapter 17. I'm sorry, okay? Also, I have realized that I need to say a couple of things sort of before we even talk about the first thing that's on this slide. So let me insert, if you want to, like a little box here, and we're going to talk a little bit here in the middle, just to give you some terminology. Just a little bit of terminology. So first of all, we may refer to the system sometimes, and other times we may talk about the environment. The system versus the environment. I'm just going to keep doing that because I'm a very irritating person. So, deal with it. All right, the system. In the case of the system, this is the focus of whatever problem we're working on. So maybe you could say that this is sort of what we're looking at. It's the focus of the problem. It's the little slice of the universe that for whatever reason we've decided to focus on and analyze and perhaps solve a problem about. Okay? The system. On the other hand, the environment is simply everything else. So we may isolate a little part of the universe that we'll call our system. We'll do a problem. Anything that's not in that system would be considered the environment for that system. Also, we may sometimes consider the state or the condition of the system. And we're going to look at this two different ways, and you will see as we go through these particular chapters, we're going to refer back to these two different sort of ways we're going to observe the state of the system. And we're going to even try to make some equations that connect the two together, okay? The first of these is the microscopic state of the system. What's happening at a microscopic level in that system? So here we're literally talking about atoms and molecules. What are they doing? What condition are they in? What is their state? And I'm really frustrated by all you people sitting in the aisle because I like to wander around and I'm just trapped. I don't know what to do with myself because typically it's like, this is my exercise time. I'll just make laps, just go up. No, it's fine. Well, it'll be okay. Thank you. But now I'm just like, I don't know where to go. So now I'm forced to just kind of sulk back down here into this little cage that's been given to me, okay? It's just sad. So the microscopic state of the system, we'll look at that a little bit in this chapter. And the other of these, well, kind of the opposite, is the macroscopic state. The macroscopic state of the system. You could think of the macroscopic state of the system as things that are directly observable by our instruments. The condition, the state, the properties of that system that we can measure with our instruments or with our senses. And these macroscopic properties are what we call state variables. These macroscopic properties are described by what we call state variables. Yay, terminology. We did terminology. Go us. We did the first thing. Okay? So let's jump over to the side there, and you can see underneath chapter 17, we've got the atomic theory of matter, which is going to be sort of the basic idea that we use to describe things in chapters 17 through 20, and we'll refer back to it often. I don't think there's anything terribly revelatory in the whole process, but let me just describe it all. The atomic theory of matter is just this idea that matter is composed of indivisible parts. I notice we're putting indivisible sort of in quotes. Can we divide them? Yeah. And maybe a better description of this indivisible is that if I divide it further, it's no longer the same substance. Matter being composed of indivisible, air quotes, pieces. Indivisible meaning that if I continue to divide it, and I can, well, now I have like constituent parts of those individual pieces, and those are something else. They're not that particular substance anymore. And it turns out that we first started to get the idea that there was an atomic notion of matter with this little thing you see at the bottom, which describes what is known as Brownian motion. And these little lines that are seemingly of, well, random length and just sort of bouncing around different directions is describing little tiny particles, specifically in this case, grains of pollen that were suspended in water. Just like in a glass of water that's just sitting there, and the fluid, the water itself, isn't moving at all. And yet, these little tiny particles inside are seen to be like moving around with this odd motion that's described by all of those lines that you see there. Now, this seemed to be a little bit inexplicable, right? It's like water sitting still. There's little particles that are inside, and it's not like pollen grains are alive, right? They're not like swimming around or something in the fluid. But yet, they're still moving around. What's causing them to move around? Well, it was hypothesized that it was this atomic idea, this idea that there are little pieces of matter in that water, and maybe, well, they're knocking the little pieces of pollen around, the little grains of pollen, okay? And it turns out that that was true. The small motion in the water of the water molecules that are vibrating back and forth are actually hitting the grains of pollen and sort of making them spring around and have this motion. It turns out that Einstein was able to use this and observe these little motions and sort of assume that every time it changes direction, it must be hitting another water molecule to get some feel for how large these molecules were. And he made some estimations. I don't really need to put that up there, but started to sort of approximate how large these atomic parts were in matter, and just using this Brownian motion idea. We are going to take this atomic theory of matter and go over here to the right. And have this basic construct that as objects get more solid, or we'll say that if objects are in a more solid state, we can assume a couple of different things. We can assume that there are stronger forces between the atoms or molecules, and there's also less motion of those atoms or molecules. As we get more solid, things are more rigid. They're more stuck in place. And I think that just makes logical sense to all of us who know a lot about atomic theory already. Okay? Yeah, this is my way of clearing the aisle, right? Like, if I do enough of this, there's going to be like at least 5 of you that are like, I can't take that guy. I really hate him. I really wish I didn't have to sit in his lecture, and then you're just not going to come back, and that'll be fantastic. We'll have space for everybody. So, I'm joking. Yeah, a little bit. As you can see, the next slide, oh, look at that. We were talking about atomic theory of matter, and all of a sudden we're just going to talk about temperature. Yay. See, unrelated, okay? But we're going to pull all this together a little bit later on. So, temperature. I think we all have the idea of what temperature is. Maybe we could describe this as just a measure of how hot or cold something is. A measure of how hot or cold something is. Nothing terribly surprising there. And we can describe temperature scales. We can make a temperature scale. Let's say they are created by making divisions between easily reproducible temperatures. We can create a temperature scale of which there are a number, some that we'll use in this class and many that are common, or you could just make your own if you wanted to. Why not? Seems like Mr. Fahrenheit did, at least. Just take two easily reproducible temperatures. For instance, the freezing point of water and the boiling point of water. It's easy to make those in the lab, so we could say that on any temperature scale that we create, it's like we know that whatever number we assign those are describing the exact same temperature. And then we can make divisions in between the two. So in the case of Fahrenheit, and I really should put these in the opposite direction, and also I feel like I should say the name Fahrenheit with a little bit of disdain, because what kind of temperature scale is this exactly? You know, it's like, okay, freezing point, boiling point, that seems like a pretty good idea. And now it's like, let's call the freezing point 32. Why? Okay. And then let's call the boiling point 212. Again, why? And let's just make divisions in between the two, and let's not make it 100 or 10 or 50. Let's do 180, because that sounds like a good idea, right? Why? I don't know. Not the best idea starting out, but it was a temperature scale. I don't know if it's apocryphal, but I heard that Fahrenheit, and maybe you can chime in on this, that this 32 was just like based on the idea that whatever 0 was lower was just the lowest temperature he could create. He's like, 0 is as cold as I can create something in my lab. Okay, let's just say that's the coldest. Seems a little Fahrenheit-centric, don't you think? Just a little bit. And then on that scale, it turns out 32 happened to be the freezing point. True or not, who knows, okay? So Fahrenheit, I think every time we mention it, we should say Fahrenheit. With just kind of a little gag at the end because I don't really care for this. Celsius, better, again, using the same two easily reproducible temperatures. But hey, why don't we make things a little more reasonable? And let's say that freezing point is at 0. Let's sort of start there and assume, like, fine, things can be colder. We'll just call those negatives, but at least we're starting at a reasonable place. And let's create 100 equal divisions in between those two easily reproducible temperatures. Yay! Great idea. Sounds at least a little bit more scientific in general. So Fahrenheit, Celsius, yeah. But number 3 will come later, which is the king of them all, right? The Kelvin scale, where things really make excellent sense. And it's the one we're going to want to use in here because, yay, physicists, all of us, yes, Kelvin scale is the best, but we'll talk about that at the end of this chapter, okay? At this point, just keep in mind that you can easily do some conversions between these two. Notice the freezing point of water for both of these. It's just 32 degrees higher for Fahrenheit, so that's the first thing that you need to keep in mind. And also, you could say that a temperature difference of 9 Fahrenheit degrees is the same as 5 Celsius degrees. Those two things together will give you the equations that you see to convert between those two temperature scales, okay? So it's only those two facts that you need to keep in mind, and you really don't need to memorize equations at all, okay? Just look at the ratio and do that conversion where they're off by 32 degrees from each other, okay? And you can see the difference between those two on the right. I don't really need to talk about that nice thermometer over there at all. Instead, we'll just move along, okay, and talk about thermometers in a little bit more detail. So let's see. Let me take a quick look at my notes here. What did I want to say about thermometers? Okay. Thermometers. The whole idea of thermometers is based on the fact, we'll say that properties of matter change with temperature. If I'm looking at a particular substance and I change its temperature, there are a lot of things that we could measure about that particular substance that change. Maybe it's something like the size, and we'll look at it in a little more detail in just a minute. Thermal expansion. If I take a solid, in general, if I heat it up, it gets a little bit larger, okay? And vice versa is true. Other things that are a little bit easier to deal with are a little bit more precise. Things like electrical resistance of materials changes with temperature. What we need to do to create a thermometer is to look at a particular property and measure exactly how it changes as I change the temperature and make a correlation between those two. Of course, I could maybe measure, say, the size of something and say, ooh, I put it in freezing water. I know that that corresponds to 0 on a Celsius scale, and I could say that, ooh, when the object is this particular size, I know that's its temperature. And then we could maybe heat it up and put it in some boiling water and say that now this thing is a little bit larger. Well, now I'm using that object as a really, really basic thermometer, right? And we could plot different points in between and try to get some feel for that. Now, of course, that's not going to work so well for most things. I can't just say, take this chair or this iPad and be like, I want you to be a thermometer, right? And I'm going to just, put you in different things and be like, oh, you changed size just a little bit. Now I know exactly what the temperature in the room is, because the chair's not going to change size that much. It's going to be very, very hard to measure. The iPad's not going to change size that much. I need things where over a reasonable temperature range, it's something I can measure. I can measure how much the size or whatever the property is of that object changes with temperature, okay? So, for instance, we could look over here at the right. We've got the basic idea of a thermometer. Maybe this red stuff in this particular thermometer is either a gas or a fluid of some type. Maybe it's a gas or a liquid. And the volume of that gas or liquid changes as I change the temperature. Well, when I restrict it in its space and the volume, it has to move a little bit. Perhaps I can see that linear change in volume much more easily. We've got a thermometer, okay? Another idea might be taking two strips of metal and attaching them together. And it turns out that if those two dissimilar metals have different expansions as I change in temperature, well, they're not just going to expand together. Instead, that thing will bend left or right because one of the metals is expanding or contracting more than the other. And maybe you could put that whole thing like on a dial of some type, and when it bends and points in a specific place, I know that corresponds to a particular temperature, okay? These aren't necessarily the best ideas. There's a lot of different ways we can create a thermometer, but there's going to be inherent problems because we could say that different thermometer types may disagree. We'll say because of how different materials respond over different temperature ranges. So maybe I create a thermometer and it's really good, say, around the freezing point of water, plus or minus a certain number of degrees. But as it gets warmer and warmer, maybe it doesn't expand in a linear fashion, okay? And then things kind of get screwy as I get closer to maybe the boiling point of water, all right? And maybe I have another kind of thermometer that uses a different material, and it's like, oh, it's good at higher temperatures, but not so good at lower temperatures. Now all of a sudden it's like, oh, now I got to pick a different thermometer depending on what I want to measure. That all just sounds kind of sad. So what we can do is use this little concept over here at the right, the constant volume gas thermometer, which you could think of as sort of a standard thermometer type. The constant volume gas thermometer. And we're going to refer back to this later in this chapter, and if I remember correctly, in some upcoming chapters as well. Let's just zoom in on the constant volume gas thermometer and talk basically how it works, okay? Just think of this as sort of a schematic. It's not necessarily going to look exactly like this, all right? We've got some gas. Notice it just says gas because it doesn't matter what type of gas. This works in all gas types, okay? And we've got some gas that's trapped in there with some mercury here, and we've also got some mercury that's over there, okay? If we put this reference mark here, then I have a specific volume of gas that's trapped, okay? If I remove the mercury and just let it do whatever it wants to do, if I heat the object up or if I heat the gas, let's draw that in here. What do you say? Fire. Why not? That's beautiful fire, don't you think? You're going to learn quickly this semester that I can't draw or that I'm the best artist in the world. Evidence so far suggests perhaps the first case, I guess. All right, so we've got some fire. We heat this up. If we just let the gas do what it wants to do, it wants to expand. Okay, it's going to take up more volume. So what we can do is try to keep it the exact same volume by taking this whole right side and lifting it up. Okay, when I lift this up, I'm moving the mercury up here to a higher level, which is going to create more pressure back over toward that reference point and on the gas. Okay? So what we do is we raise this side to raise that mercury level until we make sure that the gas stays at the exact same volume, so that that transition from gas to mercury is back at the reference point. When I do that, you could maybe pretend that this level of mercury is up against some sort of scale that we've previously calibrated. And based on the height of that column of mercury on the right, we can measure the temperature of the gas. Okay? By keeping the volume constant, we move the mercury up or down to counteract its desire to expand, and we can calibrate that to known temperatures and to a known temperature scale. Okay? Keep this constant volume gas thermometer idea in mind as we go forward and talk about some gases later in this chapter. Okay? It's also going to relate back to the Kelvin scale and how we can describe an absolute temperature scale. All right? So let's see. That's thermometers, which brings us to the 0th law of thermodynamics. So before we do that, we've had a couple of transitions here. First of all, we talked about some initial terminology. We switched over to atomic theory of matter. We talked about temperature and then thermometers, which is all kind of associated. This is going to build on that idea, but it also feels like a little bit of a breaking point. So here's what I want you to do. Take a deep breath. Are you holding it? I didn't tell you to breathe out. I just said take a deep breath. You good? Okay. Now turn around and everybody exhale that way, because I really don't want all your germs coming this direction. You know, you people are just sick. You know, college campus is like this breeding ground for just disease. And personally, as a germaphobe, it's terrifying. It's really quite awful. Which, electronic homework, that's really good for me. Because, like, yeah, so, you know, all of you are going to get the flu, and it's going to spread around, and I'm terrified already. Please go home. I don't want to hear about it. All right, so let's talk about the 0th law of thermodynamics. First of all, the 0th law, yeah, you got to love that, right? Who named something the 0th law? Well, it turns out that this law was sort of put together, and the idea was presented after we had the other laws of thermodynamics, right? So it's like, first law, second law, third law, and it's like, ooh, we've got a new one. Should we call it the 4th law? Well, maybe not, because it is more fundamental than the other three. So think of this as, well, it came later, but it's more fundamental, so it really needs to be first in the list. Therefore, we get the name 0th. Aren't you glad they didn't start 0, 1, 2? Otherwise, we'd have a negative first law of thermodynamics, and that would be extra ridiculous. So it's kind of nice we don't have that. There's not too much to talk about here because the 0th law is ridiculously obvious. In fact, it's really just a mathematical principle, all right? Notice we've got two different blocks here, A and B. It turns out if these two blocks, if they're at the same temperature, in other words, if they are in thermal equilibrium, so we've got an abbreviation there, TE, that's thermal equilibrium. If they are in thermal equilibrium, meaning they're at the same temperature, there's no heat flow between the two, okay? If I then take this block B and touch it to block C, a completely different block, and there's no heat flow between them, and they are at the same temperature, then I can sort of step back from this whole thing, and it makes perfect sense that the first block and the last block must also be in thermal equilibrium or at the same temperature, okay? So it's just if A is equal to B and B is equal to C, then A is equal to C, right? So it's like, why did we really need to state this? Your question. Which concept is more primitive? Tell me more. Yes. I don't know that I could say which is more primitive, just the fact that they are, temperature is completely determined by thermal equilibrium and vice versa. So, primitive, I don't know. I'll let you do your own research on that. I'm sorry. Anybody else? Okay. So thermal equilibrium is dependent totally on temperature. The nice thing about the 0th law of thermodynamics, if you think about it just a little bit more, this law allows the use of thermometers at all, right? Think about how you use a thermometer. You take your thermometer and you put it in contact in some way with the thing that you'd like to know the temperature of. If the 0th law of thermodynamics wasn't true, that wouldn't be a way to measure temperature, right? The idea is I can take this thing, put it in thermal contact with this other thing that I want to know the temperature of, and we know that if they are at the same temperature, there is no heat flow between them, meaning that the thing that the thermometer reads is the temperature of the thing that I'd like to measure, okay? If this wasn't true, thermometers would have to come from a different place or a different perspective altogether, all right? This is what allows thermometers and allows us to measure temperature altogether. So, let's see. You all tell me a few things. I'm trying to get things straight in my head. I see a 2:58 time. Agreed? Yeah? We started at 2:10 Berkeley time. Yes. What time does this class end? 3:30. Okay. I'm going to make today's lecture a little bit on the short side because A, it's the first one. And what do you expect the first week? Syllabus week, you know. Yeah, I know. Plus, we built a little extra time in the first week because we have today and Thursday to cover chapter 17. Okay? So what I'd like to do is cover this next topic. We're going to talk about thermal expansion, and that's going to sort of be the cutoff, and we'll pick up things on Thursday. Does that sound good? I'm looking around at you, and you look warm. Just sort of in general, because we're like extra crowded today. You people are sitting on the steps. You're standing up back there, and you're already like starting to do this a little bit. Like I see it's happening. And all of you in the middle just look warm and sleepy at this point, and that's not good. So I'm telling you this to let you know that if you could listen just a few more minutes, I'm going to let you go early on the first day and the first day only. Okay? You just got to stay with me a little longer. Can you do that? All right? So I'm going to leave you people over here. I'm going to go bother the people on the other side of the room a little bit because you are sick of me. All right? So let's talk a little bit about thermal expansion. Just a few slides on this, and then we will move on. Did I see a hand over here somewhere? Or you just put your sweater on? You're good? Okay. Wow, I didn't know there's people sitting in the aisle over here, too. Hello. Welcome. Yeah, there's a chair right down front. No, stay where you're at. That's just mean. All right? Thermal expansion. We've already talked about the idea just sort of casually that if I heat something up, in general, most things get larger and vice versa. So we're going to start by talking about thermal expansion of solids. And we're going to have to deal with fluids a different way. And we're going to do that part of it on Thursday. Thermal expansion of solids. So let's start by just writing out specifically the thing that we've already said, that most materials expand when heated. Most materials expand when heated. By the way, this side of the classroom, I'm not going to look over there. Do they look relieved over there now? They're like, I'm glad he left. They do? Uh-huh. And I'm seeing how all of you look. You're like, please go away. See, don't you wish the aisles were clear and then I could just sort of keep moving and life would be good? And we'd end up with like a nice air current in the room, too. I serve as a fan. It's fantastic, all right? Most materials expand when heated. Let me give you a couple of equations and we'll describe these in a little bit detail. So we're going to start by talking about linear expansion. Linear expansion, we could write as something like this. Delta L is equal to L initial times alpha times delta T. So the change in the length of an object is equal to its initial length, what it starts at, times some constant alpha, which is the coefficient of linear expansion. So I'm going to draw a little arrow here instead of writing that out and say, ooh, there it is, coefficient of linear expansion. And then delta T is just, of course, how much the temperature changes. So the starting length, the coefficient of linear expansion, which is different depending on the material, and how much the temperature changes. Notice at the top there it says that these are coefficients of expansion near 20 degrees Celsius, which implies that you would get different coefficients of expansion at a different temperature. So yes, these problems can get quite a bit more complicated, and if you had to be designing something where expansion was really important and you need to know something about it over a large temperature range, it isn't quite this simple. You're going to need to know something about the coefficients of expansion at all of those different temperatures. So what we're doing here is sort of just using an average value over a particular delta T. And we're not going to do anything more complicated than that in this class, okay? Just keep in mind that there is a more complex situation that's hiding out there, all right? Let's see. The second one of these that I want to talk about just a little bit is volume expansion. We could look at area expansion. It kind of works the same way, but I don't want to spell that one out. Volume expansion looks like this. Big surprise. The equation sets up exactly the same, except we have a different expansion coefficient there in the middle, and you can see that's a coefficient of volume expansion, which we have in the right column on this slide. There is a secret shortcut between these two if certain conditions are met. Let me put that here at the bottom. We can say that beta is equal to 3 alpha. So the coefficient of volume expansion is 3 times the coefficient of linear expansion if alpha is independent of material direction. And by material direction, I mean if you have, maybe sort of a cylindrical piece of something. We're talking about length versus its thickness versus whatever the third direction is that you want to call. It's independent of material direction. Meaning if I take something and I create a temperature difference along the length that you see there, I get a certain expansion. And if I spin it around and, say, create a temperature difference this way, it expands the exact same amount. And then perhaps into the screen and out, if I look at the thickness of it and I create a temperature difference that direction, it expands the exact same amount. Meaning the direction of the material doesn't affect how much it expands, okay? If that is true, well, then the coefficient of volume expansion is just 3 times the linear coefficient, all right? Another way of describing this is we could say that the material is isotropic, and it is not anisotropic. Anisotropic would describe it having different properties along different axes, different directions. Hey, I'm back over here now. I don't know how that happened even. Clearly, I have a natural side of this classroom for some reason. Okay? Let's see. Sliding over a little bit, here is one example of something we already talked about, the bimetallic strip, which is simply 2 different metals, and they have different coefficients of linear expansion. So if you can see in that first pane, which, there's B and A, okay? If we chill that particular piece, then B is going to shrink more, which, if they're actually physically bonded, makes this thing bend, and it bends the opposite direction if I heat it, all because of different coefficients of linear expansion, which if I put that in an electrical circuit, you can imagine a case where maybe this is straight until it gets colder, and then it bends down and makes this contact to some sort of electrical circuit that does something. Perhaps this is something like, a more old-fashioned thermostat in your house, right? If you take the little white box off and look inside, you might see something that looks like this, which feels like a little bit of a hack, right? It's creative. Like you literally have this physical thing that changes its shape depending on what the temperature in the room is, which is kind of cool. And, you can take this other contact and move it up and down with that little knob on the outside, meaning I don't want the air conditioner to come on until it bends this far, and this far may correspond to, 65 degrees Fahrenheit or something, okay? It's creative, but it feels a little weird. So now we have digital thermostats, etc. But you get the idea. This was used for a long time. I will end on this slide just because it amuses me. Yeah, so there on the left we've got bridges. You've seen things like this, whether it's on a bridge or maybe just gaps in a sidewalk that are accounting for expansion and contraction with temperature. You really want your bridge to be able to expand and contract and have space to do that, which you can see there's space that's provided there. If you didn't have that, the bridge is going to buckle, bad things happen. But I love the case on the right of these pipes where apparently there's a lot of expansion that happens. So they just took some extra pipe and said, let's just kind of smush it together and it can expand out as needed, which is kind of cool. So we will pick things up on Thursday when we talk about water and other fluids and their expansion. We were talking about thermal expansion of solids. We had just about finished the topic when we decided to close out class. So we've got these two equations. There's nothing terribly complex with them, I don't think. We talked a little bit about one example with the bimetallic strip. We looked at a couple of pictures here where things are just odd, especially on the right. But the one thing that I left off was talking just briefly as an aside about water, because water is just a little bit strange. You've got here two graphs. This top one is a zoomed in portion of this bottom one, and this is a graph of the density of water versus temperature. And we all know from what we talked about the other day that, well, things should expand as they get warmer and contract as they get smaller. If it's contracting, then its density is increasing, which is exactly what we see happening for the most part, right? The density is going up as the temperature goes down because it's contracting. But if you look at just before the freezing point, so here now we're looking at 6 degrees Celsius and then 4 degrees Celsius, instead of continuing to rise, it flips directions. It starts to expand because the density is now dropping, okay? The molecules are getting farther apart. As it continues to approach the freezing point, the density continues to drop because it's expanding, which is backwards from what it's supposed to do. If we continued to look at the density even as it goes through the phase transition and becomes a solid and turns into ice, we would still continue to see the fact that the density is going down. Even as it goes through the phase transition, it continues to expand, which is kind of nice for a few different reasons. Primarily fish. Fish, right? Fish live in water. Imagine a lake, and we've got a situation where the temperature is dropping, and eventually the water begins to freeze. Well, of course, the water on the top is most exposed to the atmosphere, so the water on top is going to freeze first. If this didn't happen, well, then it would become more dense as it froze, and it would be more dense than water then, so the ice that formed on the surface would drop to the bottom of the lake. And the fish would, of course, just be like, oh, ice is coming, right? Swim around the ice. I don't know. I guess that's what's happening. And they're like, well, my lake is now a little less deep, but I'm still alive. Until more freezes, maybe it stays cold for a long period of time. More of it freezes on top, ice falls to the bottom. More of it freezes on top, ice falls to the bottom. And then the fish start to get a little antsy, right? Now the lake is only so deep. What if it stays cold for a long period of time and freezes completely through? Well, what do you end up with? A lake, I guess, with just a bunch of fish laying on top, which is just sort of sad and depressing to think about. If water behaved the way most everything else did. But instead it goes the other way, right? Water gets less dense as it becomes ice and just stays on the top. So the lake, instead of freezing from the bottom up, freezes from the top down, giving sort of a thermal barrier for the fish, and they always end up with a little bit of water at the bottom so they can stay alive through the winter, which is kind of nice. All because of a quirk in the thermal expansion of water and ice. Weird? A little bit. Why is it this way? Crystal structure stuff. Why did it get that way? Who knows? Someone smarter than I would have to philosophize about that. So, water's a little weird. What we would like to do now is not use clickers in this class. So I am going to propose questions to you pretty often. What we're going to do in here is you can just vote with your hand, right? 5 options. You can easily vote with one hand. So read the question. When you think you have the answer, just maybe a hidden vote in front of you so you're not giving away your answer to everybody else. And when I see enough people voting, we'll talk about it and move on. Clickers are terrible, aren't they? Who loves clickers? Ooh, wow, that was impressive. Who hates clickers? Why do you hate them? I have my own reasons. Because it makes you come to class? Maybe that's the first one, yeah. It's kind of a logistical nightmare, getting the grades. It's like, oh, I was absent this day. What's going to happen? I was sick. And it's just a nightmare. So, has anybody voted yet? I'm looking for hand votes out there. It's clearly not number 5. At least it shouldn't be. I didn't write these questions, but there's always a ridiculous answer. I think we're probably on the same page that if we were to run hot water and try to keep it mostly on the outer one, it's going to expand, or at least expand more than the inner one, because the inner one's going to heat up a little bit less, which would allow us to get them unstuck. Of course, you could break them, but then you don't have glasses, so what's the point of that? All right, take a moment with this one. This one might fool you just a little bit more. Oh, look, I can walk down through here today. There's nobody in my way. Ha ha ha, you people in the back can't escape. I will hunt you down and say hello. 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 There's even a couple of spare seats back here. I should just sit down. I can lecture from anywhere. Looking for votes. Who's got votes out there? Yeah, let's see. I see some ones. I see some twos. I see a good bit of threes. So first of all, let's see. We take the tape measure outside on a hot day. What's going to happen to the tape measure? You can all say it at the same time. Go. It's going to expand. So let's say maybe, I don't know, there are markings on here, and this is 1, and then over there farther is number 2 or something. And of course, there's a bunch of little markings. All right? And then this thing is going to get larger. It's going to expand linearly such that maybe if it was measuring a meter or an inch or something before, now that exact same piece that says 1 inch or 1 meter is bigger than it should be. So what does that mean for the measured lengths? They are going to be too small. What you measure is going to read a little bit too small. If you imagine maybe, let's put something next to this that we're actually measuring, right? And let's say it reads 1, 2, 3, 4, 5, 6, 7 before. Just keep in mind that number 7 is going to move over this way a little bit, which means now it's going to read 6 or 5 or something smaller, okay? Measured lengths will be too small. I think this microphone's working now. It's kind of weird. I feel powerful. I don't know. Question? It is. So we would have to explore that more deeply depending on what object we were measuring. Anyone else with questions? Number 3, we've got one more of these, I think. One more, or 2 more actually. Yeah, talk to people around you if you'd like, or answer all the questions yourself. That's fine. Confirm your answer with someone nearby. All right, who votes 1? 2? 3? Okay, a little bit mixed. 4? Anybody? Somebody? Yeah, I figured some of you really want 4. So I think the first instinct here is to say, oh, well, maybe it's going to expand into any open space it can find. Okay, and you might want to say that it gets smaller, or maybe you might want to say it stays the same. Okay, but the truth here is that as it expands when heated, the hole gets larger too. And maybe some of you knew that just because you've seen a demonstration before, or you're like, oh, I memorized this answer at some point. Let's talk a little bit about why this is true. And here's the way that I like to think about it. Let's look at the hole itself and just pretend we're looking at one layer of atoms that are right next to that hole. Okay? If the hole were to get smaller, do those atoms get closer together or farther apart? Yeah, if this starts to move in this way, all of those atoms are going to be closer. That's not expansion, okay? For them to actually get farther apart, the only way that they can go is the opposite direction, which means the hole is going to get larger. Okay? Questions, thoughts, complaints? No? Okay, let's do one more. No, there's two more. How many of these are there? I'm tired of this. All right, fine, two more. Clearly, number 3 is the answer. If I stand right here, I can simultaneously lecture and listen to another lecture. I don't know what that's about. All right, who says 1? I like it. We'll go with number 1, okay? Just looking at the relative coefficients of volume expansion for these objects, notice that aluminum has a greater expansion coefficient, which means if I just give them both the same temperature change, it's going to expand more, meaning that the holes that's holding the screw is going to span more than the screws themselves, which means you'll be able to get the thing apart, okay? Questions about that one? We'll do one more, and for this one, I think I need to give you an equation that you might have had last semester because it deals with a pendulum. The period of the pendulum is equal to 2 pi times the square root of L over G. Vote with your fingers when you think you have it. How's it going back here? Everybody alive still? It's a lot warmer back here than it is down front. I'm sorry. Get here early and take those seats. Okay, I think you're starting to converge on the correct answer. The answer should be 1. It's running slower because all of a sudden it's going to say a second is more than it actually is. Why? Well, the length of this pendulum is going to get longer, and if that gets longer, then the period goes up. Okay? And I think that is finally all of those questions. Does anybody have anything you want to say about expansion of solids, thermal expansion of solids, before we switch gears? I think I've found the perfect place to talk from. This is it, right here. This is fantastic. Except for you people. Look at them. Did you see those faces? They're like, why? Leave us alone. Please disappear. Too bad. I'm staying here longer now. So, we talked about thermal expansion of solids. We can't deal with gases the same way. Why? Well, gases are a little bit weird, right? If I just put gas into a space, it just expands automatically to occupy whatever space I put it in, okay? So what we're going to do is use gas laws instead to deal with thermal expansion of gases. And the reason we're going to do this is because the volume of a gas is dependent on both temperature and pressure. And volume is really what we're talking about when we're talking about the size of a gas. How much space is it taking up? So this slide and the ones that follow, let's see, at least the next two, are essentially going to be a review from some chemistry class somewhere, I'm assuming. Probably, yes. You've looked ahead. You're like, gas laws. Yeah, I know gas laws. Let's just hope that somewhere in the explanation of these, maybe there's a little physics point of view that like creeps in, and maybe you get to see them from a slightly different perspective. If not, just fall asleep for 3 or 4 minutes and it'll be over, okay? So, volume is dependent on both temperature and pressure. Let me make a couple of points before we get to these. First of all, we are going to write these gas laws, which will be relationships between different properties, or what we might call state properties. Relationships between state properties. Remember, we talked about that right on the first slide of this chapter, which means that these gas laws are going to be what we would call equations of state. They tell us something about the current properties or the current state that the gas is in. We should also point out that these are not valid in some cases. Let's say it's not valid if too dense or near the boiling point. If we're dealing with temperatures that are near the boiling point of whatever gas we're looking at, in other words, if they're near liquefaction, or if they're already really dense, then these gas laws kind of diverge a little bit and they fall apart some. And finally, it looks like I've got one more thing here. We are only going to be considering what we call equilibrium states. In other words, even as something is changing, so if we're changing the temperature or the pressure of the gas and the volume is responding accordingly, we're going to do that slowly enough that a couple of things are true. We are going to say that the properties are the same throughout the gas and not changing, which seems to be a little bit contradictory, I understand. So imagine you have a gas and we want to take a new data point to kind of see how these three properties are changing. If we make a little bit of a change, we need to wait for that gas to be in a new constant state, a new equilibrium state. So I change the temperature and I wait for the entire gas to be at that temperature. I wait for it to expand as much as it's going to, and I want it all to settle out and be at the same pressure before I change it again and take another data point. So it's like we're going from state to state, where each state is like a situation that's constant, okay? If we instead just say we're at one temperature and we just change it to another temperature and try to take data as that's happening, different parts of the gas are going to have different state variables along the way, and all of a sudden these laws don't apply and everything gets a little bit complicated, okay? So 3 things you need to keep in mind as we state these. First of all, the fact that the volume of the gas is inversely proportional to the pressure if I hold it at constant temperature. The volume is inversely proportional to the pressure. So we see that in the graph over at the right. I'm trapped. That doesn't look like a good way to go. Maybe go up here. That's just obnoxious, I know. But alas, please don't do that. There's like 6 of you who are like, I need to write that down exactly like he did. And now you're sketching that line through the words. Yeah, I caught you. I know you're doing it. Please don't. That's ridiculous. All right? So you can see that as we decrease the volume, imagine packing the gas in tighter and tighter, it makes sense that it's going to push back with more and more pressure. Okay? These 2 things are inversely proportional to each other. Or we could rewrite this a little bit and say that the volume times the pressure, or PV, is equal to a constant. PV is equal to some constant value. And of course, this is known as Boyle's law. Also, using the word law on these is a little antiquated in some way. Like, we think now of like physical laws as something that like it applies everywhere in all situations, and it's like has broad reaching implications. These are a little bit narrow because like right at the top I said we have to be a little careful. I gave you several different things that these don't apply. But it's kind of a historical thing. When they were first discovered, they used the word law, and now we just call them laws, even though really the word doesn't apply so much anymore. Okay? Number two is the idea that the volume is directly proportional to the temperature as long as I'm using an absolute. I didn't spell absolute right, did I? What's happening here? I don't know what that is. Things got tangled. Back one more. As long as we're using absolute temperature. The volume is directly proportional to the temperature if we're using absolute temperature, or in other words, if it's in Kelvin, which we'll look at a little bit later. So in other words, this graph looks something just like this. Volume as a function of temperature starts at 0 and is just linear. And I think that makes sense just from our understanding of volume and expansion so far, right? I heat something up, it's supposed to expand. When I'm dealing with a gas, it turns out that's a linear expansion. Let's see. So in this particular case, that is known as Charles' law. And I think that's all we need to say about that. Oh, except this is held at constant pressure. Let's not leave that out. And then number 3 is a relationship between pressure and temperature, and these are directly proportional to each other. Once again, this time we're using absolute pressure, so not gauge pressure. If you remember your discussion of fluids, it's not just how much above atmospheric pressure, it's the absolute total pressure, which means that we get something that looks like that. Pressure as a function of temperature. And in this particular case, we're holding the volume constant. And that is the law of Gay-Lussac. Okay? 3 different gas laws that relate what's happening to the volume, the size, as we change these other 2 variables, pressure and temperature. More is happening with gas than we have to deal with solids. But we can combine all 3 of these into one law, the ideal gas law, and write it something like this. PV is equal to N times R times T, where finally we have some constants in there, the constants of proportionality that were missing in the previous statements. PV is equal to nRT. So don't forget, the pressure and the temperature here have to be of the absolute variety, and apparently I can't spell absolute today. So absolute pressure, we're talking total pressure, and when we're dealing with temperature, it has to be in Kelvin. PV is equal to nRT. And let me point out that when we're talking about ideal gases, it means we're putting some restrictions on it. We're going to deal with real gases in the next chapter, which is actually cases where you have gases that are diverging from the ideal gas law, meaning they don't obey the ideal gas law. And this happens in cases where we have high pressure, let's say non-ideal. If high pressure, high density, or near the boiling point. Okay, cases where gases will diverge, and we would call those real gases instead. So just for completeness, I am sure that all of you have probably studied the ideal gas law. You've done labs with the ideal gas law. You've read books on the ideal gas law, right? Okay, maybe not the last one. The first 2, yes, you've done those things. Yes. Yes, do you want to vote? You've never studied the ideal gas law. Let me see that as well. You can hide your hand on that one if you want to. That's fine. Okay, you all have. Let me just, to make the notes complete, add a couple more things, and then we can move along a little bit. Okay? At least in this particular case, R, the gas constant, is going to be equal to 8.314. And in happy physics units, that's in joules per mole Kelvin, or joules per mole degree if you wanted to use Celsius, because the degrees are the same size. The amount of gas in is measured in moles. And we should also point out that this is an equation of state. It's relating P, V, and T, three different state variables for the gas. Let's see, is there anything else there that I wanted to add? I don't think so. Okay. Sliding over to one of the last things in this chapter. We can rewrite the ideal gas law, but instead of dealing with state variables, remember we said in the first slide that state variables were things we could like measure with our senses or with our instruments. They are macroscopic things, right? I can look at something and not take into account that there's like molecules that are hiding in there and just measure its temperature, its volume, its pressure. We can rewrite this to sort of relate it back to the microscopic as well, to what's happening in the inside by looking at it in terms of molecules and using Avogadro's number. So we could say that N, which is the total number of molecules in the gas, is equal to N, which is the number of moles, times N sub A, which is Avogadro's number. The total number of molecules in the gas. And then let's rearrange that to solve for N, since that's what or little n, since that's what we have in the ideal gas law so far. So little n is equal to capital N over N sub A. And then we're going to plug that in right there. Which looks a little messy, which is why we can define another constant. So this R over NA, the gas constant over Avogadro's number, is a constant of its own, and it is the Boltzmann constant, K sub B. And you could do the division yourself, or I can tell you what it's equal to. It is 1.38 times 10 to the minus 23 joules per Kelvin, which means now we can rewrite this as PV equals capital N times the Boltzmann constant times T. And now we have in the equation three state variables, a constant, and also how many molecules are in the gas. So we're making a connection back to the microscopic from the macroscopic. Questions? Anybody? Anything? I'm just curious. Who loves chemistry? Okay, you can get out. I'm kidding, kind of. Who hates chemistry? Yeah, if you were wondering why on Tuesday I was like, these aren't my favorite topics, it's because it's like we're doing physics and then we keep like, jumping into the chemistry just a little bit, not much, just kind of like right up against that line and then sort of like putting our toe in the water of chemistry and then leaving it again. There's a little too much chemistry in these first 4 chapters for my liking, and that just makes me a little sour. So you who love chemistry, maybe you're going to hate the rest of the chapters. Ooh, I don't know. I'm sorry if true. So how many of you just don't care one way or the other about chemistry? Completely apathetic. That's good. Okay. Who says physics greater than chemistry? Ah, you're just saying that. I thought so, yeah. All right, so let me ask you, we've got several questions here dealing with the ideal gas law. And for the most part, these are just dealing with proportionality and seeing how things change in the equation. So read it, vote when you're ready. I'll give you like 45 seconds on each of these. Question? I like to think so. Yeah. So let's see, two identical cylinders at the same temperature with the same gas. So I could rearrange the ideal gas law like so, and we can say that the temperature and the volume are the same. Of course, R is the same. What's changing is N, because it says A has 3 times as much gas as B. So N is higher, which means that cylinder A, the one with more gas, is going to be at higher pressure, which I think just makes some logical sense, right? If I keep the other things constant, I just cram more gas into that same space. Well, of course there's going to be more pressure because there's more of it there that's trying to push its way back out. How about another one? Again, two identical cylinders. Same pressure, same gas. It is really hot back here. Yeah. What can we do about that? Make more people leave? We could, yeah. Yeah. So let's see. This time we're going to rearrange the ideal gas law like so, because I'm trying to figure out what's happening with the temperature. So we've got the same cylinder, so we've got the same volume. It says they're under the same pressure. And A has 3 times as much gas as B. So if I want to know which one has the higher temperature, notice they're inversely proportional this time. This means higher temperature goes with less gas, which means that B is going to be at the higher temperature. Did you follow that? Or did I say it too quickly? We're still good? Okay. Let's look at another one. Whoa, wait. I can wait. Ooh, that was scary. I didn't know I could elicit such a response by a swipe on my screen. Are we okay? A little bit longer? Re-explain. Okay, I'm sorry. Gotcha. So I've rearranged the ideal gas law. So PV equals nRT is still there. It says they're under the same pressure, so P is the same. They are the same cylinder, so V is the same. And, of course, R is going to be the same. So really what we're comparing is N and T. So if N goes up, if there's more gas, the temperature has to drop because they're inversely proportional to each other. So in this particular case, if I want the higher temperature, we're looking at it the other way. If N goes down, temperature would be higher. Okay? Good. Anybody else? Swiping over. This one might take a smidge more work than the others did. Do we have any votes out there? Let's take votes this time. Looking. I see quite a few correct answers out there. All right. I think I like what I'm seeing. So you should get choice 3. Why? It says there's twice the volume, so there's a 2 in the denominator, and also half the number of moles, which means there's also going to be another 2 in the denominator, which is going to give me a 4th, as you can see in number 3, all right? And then finally, before we get to the last little bit of this, I don't think there's too much to think about here. I'd like number 4. I'm pretty sure you can't answer things like this on exams and just be like, but it could be true. You didn't tell us how much light was in the fridge. Like, no, that's not going to work, all right? So let's see. If we take a plastic soda bottle, it's empty. Is it really empty? No, it's not really empty. There's air on the inside. It sits out in the sun, heating the air inside. If we then put the cap on tightly and put the bottle in the fridge, dropping the temperature, what's going to happen to the bottle? Well, the volume should drop, right? It's going to make things compress a little bit, which means it's going to contract, and the sides will collapse inward instead of the other way around. I think that's about all I want to say about that. Which brings us to the best slide in the chapter, Kelvin. Kelvin is wonderful. Who loves Kelvin? I'm wondering if the hands that went up first are people named Kelvin. That'd be kind of fantastic. I love Kelvin. That's me. No, Kelvin, the best temperature scale, because it makes the absolute most sense, because it actually starts at the lowest possible temperature and goes up. And now that we looked a little bit about gas laws and thermal expansion of gases, we can sort of see where that comes from. Just look at a graph of the pressure versus the temperature if we were to put the temperature not in absolute terms, but in Celsius. It doesn't matter which gas we use. If we start to track what's happening with the pressure as we decrease the temperature, first of all of them are linear. And then eventually we get to a point where I don't have a gas anymore. If I make it cold enough, they're all going to liquefy. And then we just continue to trace that back. We can't make measurements where the dotted lines are, but we can sort of extrapolate and see where all of those lines were going. What was happening to the pressure of those gases as we continued to decrease their temperature. And they all converge at the exact same point. That would be a point where the gas is not exerting any pressure, none at all, which first of all seems a little bit weird, right? How can I have molecules that are in the air sort of flying around and have them not hit things and exert a pressure? So that sounds a little impossible to begin with, right? And if it were to go the other way, where it's like things are flying around and I have negative pressure, that really makes no sense at all. Then it would have to be colliding with things and taking energy from them. That doesn't make any sense at all either, okay? So this point of zero pressure seems to correspond with the lowest possible point we can reach in temperature. So they used that point on the Celsius scale to redefine it on the Kelvin scale as zero, which means there's just this shift between the two of 273.15 degrees. So TK is just equal to TC plus 273.15, and the division size is the same. Aren't you glad they didn't change it? That would kind of suck once again. Maybe someone's like, I don't like 100. I really liked that 180. That was nice. I think I'm going to use, 367 and just make my degrees just completely arbitrary. So thankfully we don't have to deal with anything like that. 2 slides left in this chapter. First of all, or is it 3? No. First of all, a comparison of the 3 temperature scales, looking at some critical points. That's just there for your reference. There's really nothing to talk about. Which is the largest unit, a Celsius, a Kelvin, or a Fahrenheit? We already know that Celsius and Fahrenheit are the same. And because there are 100 divisions between freezing and boiling of water instead of 180, they must be bigger than Fahrenheit. All right? And then finally, it turns out that if you do the calculations, negative 40 degrees Celsius and Fahrenheit actually represent the exact same thing. Could that be true for Celsius and Kelvin? Absolutely not. Haha, pun on the absolutely. Because they're simply shifted from each other. There's no place where those 2 graphs correspond with each other, so our answer there is no. And look at that. We finished a chapter. Don't you feel accomplished? It's like we barely started. Yay, we should cheer ourselves. 1 chapter down, yay! Okay, I'm sorry, but that did not match the excitement I tried to create. And personally, that's not fair. You just kind of left me there, right? Can we try that again? 1 chapter down! Yeah. That's much better. Good job.